This is the drone I built. At first glance, it might not look like much, but it's packed with features. It can carry up to 2 pounds of payload, fly for over 20 minutes, and even run autonomous waypoint missions. Best of all, the whole thing costs just $150. In this video, I'll show you how to build one yourself. We'll cover the parts you need, how to put it together, the software setup, and of course, some flight tests. Hopefully this inspires you to build and fly your own drone platform like this. But before we dive into the build, let me explain what makes this drone different. It doesn't look like your typical FPV freestyle drone, and that's on purpose. This is more of an experimental drone platform. Instead of speed, flips, and stunts, it's designed to carry payloads and sensors. Think of it as a drone with a job. This kind of setup is a great stepping stone towards commercial drones, which are built around automation and completing specific tasks, whether that's crop spraying, package delivery, or even power washing. And the best part, you don't need a huge budget to start experimenting with these concepts yourself. Now, compared to modern FPV drones, which are all carbon fiber and have sleek designs, this build looks a little bulky, maybe even outdated. That's because the design actually goes back about 10 years, when hobbyists first started putting drones together with airplane motors and spare parts. Back then, ready-to-fly drones like the DJI Mavic didn't even exist. If you wanted an aerial camera, you had to build it yourself. In fact, DJI at the time was just a small company, and one of their earliest products was this frame, the Flamewheel F450. That's the frame I used for this build, and I chose it for a few reasons. It's cheap, since it's been around forever, it's roomy and easy to customize, and most importantly, it's efficient. The F450 supports 10-inch props with old-school airplane-style motors. That combo, large props and relatively small motors, is really efficient. In fact, it's the same principle DJI still uses in their modern drones. Take the DJI Mini for example, it weighs just 250 grams, but it uses relatively large 6-inch props, giving it up to 30 minutes of flight time. Compare that to a typical freestyle FPV drone, which may weigh around 700 grams and spin 5-inch props for only about 5 minutes of flight. So for this project, we're leaning into efficiency. Big props, small motors, and a focus on endurance, because for this one, flight time matters more than raw power and acceleration. And one final note, this drone doesn't have a camera on it, but it's easy to add one on if you'd like. As it is right now, it's a line of sight drone, no video feed required. Now let's go over all the parts we're going to need. First up, the F450 frame, and I'd recommend getting the frame combo that comes with a landing gear and power distribution board. You can get these separately if you'd like, but it's usually cheaper to get all of these in a single set. The motors I'm using are 2212 size motors rated at 1400 kV. This kV rating is a little bit on the high side, so I'd recommend picking up 1200 kV ones instead. These cost just $5 each, and I'd recommend buying 5 of them. We only need 4, but it's a good idea to get that one extra one just in case one is faulty or breaks. The propellers are 8x4.5 slow fly airplane style propellers, which are a good match for the 1200 kV motors. If you want even more efficiency, go for 9x4.7 props with the 1000 kV motors. The speed controllers I'm using are these generic 40 amp airplane style ones, which also cost just $5 each, and again, I'd recommend buying 5 of them. I got the ones with the XT60 connector and motor bullet plugs pre-soldered. They only cost like $1 more, and it'll save a lot of time when it comes to soldering. For the flight controller, I'm using the SpeedyBee F405 Wing Mini. This is normally intended for RC airplanes, but it'll work great on our drone. I chose this because it's cheap and it has standard servo-style connectors that our speed controllers can plug right into. You should be able to buy this for $30 to $50 US depending on which country you're in. The radio system we're using is Express LRS, so we'll need an Express LRS receiver, which usually costs around $10. Our drone is going to need a GPS unit to track its position, and I'm a fan of the HGLRC M100 module. Make sure you get the full-size one, not the mini one, since the mini one doesn't have a compass. There's also a new M100 Pro module. I haven't tried that one yet, but it uses a cheaper chipset than the non-Pro module, so I think the non-Pro is actually better, and so I'm sticking with that one. For battery, look for a 3-cell LiPo that's around 5000 mAh. This size is really common with RC cars, so you should be able to find one of these batteries fairly easily. I'm using the Softcase 5000 pack that is short enough to fit in the frame. Watch out for some hard-cased packs, since sometimes they can be too tall to fit inside of the drone. Those are all the major components we need, but here's some small odds and ends that I'm going to use as well. M3 plastic standoffs to mount the electronics. An airdropping servo release mechanism and a MG995 servo to operate it. A bunch of XT60 connectors and 14-gauge silicone wire. If you don't have an Express LRS transmitter, I'd recommend the Radiomaster Pocket or Radiomaster Boxer with Express LRS. If you don't have a charger, I'd highly recommend the Hoda D6. That's all the gear, so let's get on with the build. The F450 frame kit comes with 4 arms, a large bottom plate, a small upper plate, and 2 sizes of screws. The small screws are used to put the frame together, and the larger screws are used to attach the motors to the arms. Let's start off by flipping the arms upside down, placing the large bottom plate over the arm, and attaching them together using 2 of the small screws per arm. I'm using a little electric screwdriver here. It's really handy and it'll save your wrist since we have a lot more screws to go. Next, flip it right side up, place the top plate on top, and use 4 small screws per arm to attach the top plate. It's a really simple but effective design. These plates are actually printed circuit boards, and it's possible to use them to distribute power, but in practice it's way too easy for the plates to flex and crack the solder joints off, so we won't be using that feature. Now you should have a completed frame. The colors of the arms don't really matter, as long as you keep track of which way is front. For my build, the 2 red arms indicate the front of the drone. Next, it's time to install the motors. These are airplane motors, so they come with firewall mounts and propeller collets. Keep the collets handy since we'll use those later, but we won't need the X-shaped firewall mounts and screws. Instead, use the large M3x6mm screws from the frame in order to attach each of the motors to the arms. Once complete, your drone should look like this, a bare frame with 4 motors. Next, it's time to install the speed controllers. The ones I bought have the bullet plugs pre-soldered, so I just need to plug them into the motors, no soldering required. The wires are a little on the long side, so I'm looping them around the arm once to keep them tidy, and then I attach the speed controller to each arm using a zip tie. Once complete, your drone should look like this. Now it's time to install the power distribution board. This board will take the power input and split it to all 4 of the speed controllers. There are pre-drilled holes in the top plate and the distribution board. They all line up perfectly, so all we have to do is space them apart by using these M3 plastic standoffs. If you have metal standoffs, you can use them too. You just have to be a little careful since these are all conductive circuit boards. Once the power distribution board is on top, we need to solder XT60 connectors for our speed controllers to plug into. I found that it was easiest to just plug in a male XT60 connector into each speed controller and then use my soldering hands to hold it in place above the distribution board. I'll post a link to my entire soldering setup in the description below. Once complete, it should all look like this. We still need to add the main power cable, but we'll do that after mounting our flight controller. I want all the space inside of the frame for the battery, so I'm mounting the flight controller on top of the power distribution board. To do this, I 3D printed a square plate with holes in it. I'll post links to the free STL files in the description below. If you don't have a 3D printer, this is a simple enough design to cut and drill out of plastic or wood. Mount this plate above the board using more standoffs, and once complete, it should look like this. Now, before we continue, we have to set the direction of the motors. Now, these speed controllers are a little bit on the dumb side, so these won't be able to reverse the motors themselves. They only spin one direction, and so we're going to have to manually reverse the motor direction by swapping 2 of the wires if it's spinning the wrong way. So first we have to decide which side of the quadcopter is front or back, because right now there's no real direction. I'm just going to choose the red arms as the front, and by default INAV spins these props in, so that means this motor is going to spin clockwise, this motor is going to spin clockwise, this motor is going to spin counterclockwise, this motor is going to spin counterclockwise. So the props spin in towards the front and they spin in towards the back. Now to check which way the motors are going to spin by default, I'm going to use a 3-cell or a 2-cell battery. I have a 3-cell battery here and a servo tester. These servo testers are really cheap. It's like $2 and it's used to control servos or dumb speed controllers like these. I'm going to start by unplugging it from our power distribution board. I'm going to plug in the signal cable into the servo tester, and I'm going to plug in my battery. Seems like we might have a defective motor or speed controller here, so that's the issue with these super cheap, $5 speed controllers, $5 motors. You might get a dud, so one of these is a dud. I'm gonna set that aside for now. Let's try a different one. Once we get a known working combo, then we can do a process of elimination to figure out what's exactly wrong. Let's try this one. 1,000 should be off, and now a little bit more and it should start spinning. That's what we want to see. Now I can lightly put my finger on it to see which direction the motor's spinning. That's spinning this way, which is the wrong direction. And so to fix it, we just have to flip any 2 of these wires. So I'm just going to unplug this wire here, unplug the red, and then we flip them, exchange those 2 connections. And now this one should be spinning counterclockwise, which is the correct direction.
And it is. Good. So that one's all set and good to go. We still have our dud one over here. We'll get around to that later. This one is working. And that one's spinning the right direction, so nothing we have to do there. This one's spinning the wrong direction. So once again, we're just going to flip any two of these wires. Just grab the black wire here, the yellow wire here, and I'm going to exchange them around. Now it's spinning the right way. Alright, so all that's left is our problematic motor and speed controller. So what I'm going to do is I'm going to unplug this motor and I'm going to plug in a different motor. So if this setup works now, then we know that it's probably the motor that was bad, and I'll get rid of this old broken motor. If this setup still doesn't work, then it's probably the speed controller that's bad, so then I'll get rid of the speed controller, get a new one, and use the existing motor. Pretty unlikely that both the motor and the speed controller are bad. So let's test it out. Let's see if this new motor fixes the issue. There we go. So the motor is spinning up properly, and so that means that this motor here is bad. So I know this one is a bad motor. I'll replace this motor with this motor.
It's finally time to set up the flight controller, the F405 Wing Mini. This can get a little confusing because it's a 3-layer circuit board sandwich and there's 2 different options for shield plates. I'm using the smaller of the shield plates. SpeedDB provides great instructions on how to put it together, so I recommend reading it over before giving it a shot. Once assembled, it should look like this. The USB port is located on a separate board. Use the included cable to link them together. And right now, since it's easily accessible, let's update the firmware and calibrate the accelerometer. Alright, I have INAV Configurator 8.0 open, so let me go ahead and plug in the flight controller. Alright, the flight controller is plugged in. If your flight controller software is already on version 8.0 as well, then there's no need to update the firmware, but let's pretend it's not, so let's go ahead and go over to Firmware Flasher, and it should auto-recognize as SpeedDB F405 Wing. If it's not, you can manually select it over here, and then we want to set the firmware version to the latest one, 8.0.1. We can do that. I'm going to hit Load Firmware Online. This should load the firmware, and all these other defaults should be just fine, and we're going to hit Flash Firmware. It should automatically go into DFU mode up here at the top right. If this doesn't work, the most common issue is that UART1 is occupied. That's the UART that the receiver is already on, so you just have to make sure that whenever you're flashing the firmware on these boards that there is no RC receiver plugged into your flight controller. So that's why we're doing it right now when there's nothing else plugged into the flight controller. It's the easiest way to update the firmware. Okay, we get programming successful, which is good. So now we can connect to the flight controller. And now just for me to start fresh, I'm going to hit Reset Settings. So we're on a fresh firmware with completely fresh settings. It's asking me for default values, and what I'm actually going to do is I'm going to hit Keep Current Settings. I know it says not recommended, but it's going to work fine for us. So we're going to hit Keep Current Settings. Now we're going to go into the Calibration tab, and then we're going to calibrate the directions of our accelerometer. So I'm going to hit Calibrate Accelerometer, and then we just have to move the flight controller in all of the 6 main directions. So first is just straight up level, and then I'm going to move it on its various different sides. Alright, the calibration is completed, so I'm going to hit Save and Reboot. Okay, next let's go to the Mixer tab right below. Here we're going to prepare our motor outputs. We want our motors on these first 4 pins, S1 through S4, so that's timer 4 and timer 3. So under these, I'm going to move these from auto to motors. Timer 3, motors, timer 4, motors. Let's go ahead and do save and reboot. Alright, now that the motors are set up for timers 3 and 4, we're going to use the motor mixer wizard to assign the motors to those first 4 pins. So I'm going to hit that. And by default, it's going to assign motors 1 through 4, and I'm just going to hit Apply. And perfect, we have motors 1 through 4 on outputs S1 through S4. That's great, so I'm going to hit Save and Reboot. And that's all the configuration we need to do right now, so I'm going to unplug it, I'm going to hit Disconnect, and then we'll get on with the build. Now that the flight controller is set up, it's time to break out the soldering gear. Take the flight controller apart to make it easier to access the soldering pads. Switch your soldering iron to fine point tip because we're going to be soldering a bunch of small header pins. Take the 4-conductor white header pin and insert it into the underside of these 4 holes here. It's kind of hard to see, that's my bad, sorry, but trust me, they're there. Take care to put it on the correct side of the board, since this flight controller is designed so that you could solder it to either side. These 4 pins are the UART1 pins, and this is where our Express LRS receiver will connect to. Start by soldering the T1 pin on the end, then move into the R1 pin, then the 4V5 pin, and save the ground pin for last. Since the ground pin is on a large ground plane, it can be a little tricky to solder to. If I overheat the ground pin, there's also a risk of it melting and moving around, so I plugged in a random female header into the underside in order to keep it in place. Then I had to use some liquid flux to get the heat to spread and solder it properly. Once complete, it should look like this. I got a little extra solder on the S7 pad, but it's not shorting with any other pad, so it's not a huge deal. You're looking at the bottom of the board where we're soldering, but here's a look from the other side on what it should look like. Next, grab the large set of right angle header pins and insert it into place. Because of the extra solder I accidentally put on the S7 pad, I have to melt that solder while pushing the pins into place. If yours is all clean, you should be able to just place it in and start soldering. Start with a row of S pads, which should be pretty easy to solder. Then do the row of V pads. And finally, do the row of ground pads, which should be a little more difficult, so you may need flux or to switch to a slightly larger tip on your soldering iron. Once complete, it should look like this, and from the other side, it looks like this. Assemble the flight controller again, which should look like this now. Now it's time to mount the flight controller onto the 3D printed plate. To mount it, I'm using some double-sided sticky gel tape, which will also help to reduce any high-frequency vibrations. On my drone, I decided that the red arms are the front, so I'm mounting it with the pins pointed out the back towards the white arms. It should now look like this. Next up is to wire the power cable. How this works is power goes from the battery into the flight controller, and then the power goes back out of the flight controller and into the power distribution board that we wired up earlier. This setup lets the flight controller measure the amount of current being drawn. So first, let's wire up the power in between the flight controller and the distribution board. I'm using 14 gauge silicone wire in black and red. I cut 2 short lengths of it, strip the ends, and tin the ends with solder. Then I move the flight controller aside while I solder one ends of the wires to the distribution board. Then I move the flight controller back into place and I solder the other ends of the wires to the flight controller. Once complete, it should look like this. Finally, it's time to solder the battery connector to the flight controller. I decided to use the spare XC60 cable that I had already wired up. Solder this to the outside power pads on the flight controller. Once complete, it should look like this. Next, we have to plug in our speed controllers into the flight controller, but before we do so, we have to disable the BEC on each speed controller. What this means is to disconnect the center red connector from each speed controller. Because these are normally airplane speed controllers, they output 5 volts on this red center wire, usually in order to power the airplane's receiver and servos. But since we're using a flight controller, we don't need this power, and actually leaving that wire there, it can interfere with the regulator on our flight controller. So what I'm doing is I'm depinning the center red wire from each speed controller, and then insulating the exposed pin with some heat shrink. Now it's time to plug in the 4 speed controllers into ports S1 through S4 on the flight controller. The brown ground wires go down, while the orange signal wires are on top. Here is the diagram for the order to plug them all in. Speed controller 1 on the bottom right of the drone gets plugged into S1. Controller 2 at the top right is S2, controller 3 at the bottom left is S3, and controller 4 at the top left is S4. Once they're all plugged in, it should look like this. Note that the very leftmost pin isn't S1, it's actually S-bus, which we aren't using, so that pin should have nothing plugged into it. Now it's time to wire up the Express LRS receiver. The flight controller comes with this 4-pin female header with wires that's intended for the receiver. This will plug into our 4-pin white header that we soldered earlier. It's important that our receiver is on this removable header plug, because if we ever want to update the firmware on our flight controller, we actually need to remove this receiver, so this header plug makes that very convenient. The black wire goes to ground on the receiver. Red goes to 5 volts. White goes to T or TX, and then yellow goes to R or RX. After soldering the connections, use the heat shrink included with the receiver to protect it. Once complete, it should look like this. You can now plug the receiver into the flight controller, taking note of the orientation, ground side to ground side. We now have all the components we need to take it on its first flight, so before we put the props on, let's head back to INAV Configurator and finish setting up the drone. Alright, let's get started by plugging in the USB cable into our flight controller. It's plugged in, now we can hit connect. Now in the previous steps, we already calibrated, so that's all checked off. We already set up the mixer, so motors 1 through 4 are set up on S1 through S4, so that's good. Next, we're over here in the Outputs tab, and we have to set the proper ESC protocol. Because we're using these older airplane-style ESCs, the proper protocol we want is Standard. Then we do not want the stop motors on low throttle, so we're going to uncheck that. And then for motor idle power, we're actually going to need a little bit more, quite a bit more, so we're going to move that from 8% to 25%. Those are all the changes we need, so we're going to hit Save and Reboot. Next, let's go over to the Ports tab. Over here, the defaults should be fine. Our receiver is already on UART1, serial RX, that's good. In the future, when we add the GPS, that's already on UART3, that's good. And UART6 over here, that's for the wireless Bluetooth configuration, which we aren't using, but we can just leave that there. So nothing to change over here in the Ports tab. Now let's go to the Configuration tab. The only thing we need to do here is we need to enable motor and servo output. We're going to hit check that to yes. That automatically gets unchecked when you flash new firmware. So we're going to hit enable motors and servo output, and we're going to hit save and reboot. Now, assuming your Express LRS radio was turned on from the start, we can go over to the receiver tab, and we should be able to jiggle the sticks and see a response in this receiver tab. If you don't see this already, then you may have forgotten to turn on your radio. In general, you have to turn on the radio first and then plug in the flight controller via USB, and then they'll sync up. You have to bind your Express LRS transmitter to your Express LRS receiver. There's a bunch of different ways to do that. What I like to do is I like to set the binding phrase using the Wi-Fi method, but there's also a couple different ways. Probably the easiest way to do it is to unplug and plug in power to the receiver 3 times in quick succession. Then the receiver is automatically in binding mode. And then in your Express LRS transmitter, you go into the Express LRS Lua script in your transmitter, and you can hit bind from there and then bind it to your receiver. Binding your Express LRS transmitter to the receiver is one of the most common questions in the FPV drone world, and so there's a lot of resources online available to help you bind your receiver to your transmitter. Anyways, we can jiggle the sticks to verify it's working, so we have roll, pitch, yaw, throttle, and what I set up on my radio, you always want arming on channel 5, so right now it's disarmed, and if I hit my channel 5 switch, armed, it goes to armed. Disarmed. So disarmed is low, 1000. Armed is high, 2000. And then for angle mode, I have it set on another switch. So by default, angle mode is on for 2000. Acro mode. And acro mode is 1000. For this kind of drone, you may not even want to really fly it in acro mode. It's just fine in angle mode all the time since we aren't doing any like flips or stunts. And we want to switch for GPS position hold, and I have that set up on channel 7 over here. So that'll be 2000 high, channel 7 for GPS position hold. Okay, so we visually see over here that it's recognizing all of my radio buttons. So let's go ahead and set that up in the Modes tab. Our Modes tab should be blank. If it's not blank, then you can hit the X to disable everything. We're here starting from scratch, so let's add our arming to aux 1 or channel 5. That's the first one right here. And it should always be the higher end of the range. Remember earlier I said it was 2000 for armed. That's fine there. And then we want angle mode on the next one, channel 6. Acro mode, angle mode. And that's all we need. Later on, when we add the GPS, we're going to do the position hold, but since we don't have a GPS unit yet, we're going to leave that out. So we just have arm and angle mode, and we're going to hit save. And that's all we need to do for this initial setup of the drone. It's time to install the propellers. Find the plastic retaining ring that best fits the aluminum propeller collet. Clip the ring out and place it onto the propeller. Loosely assemble the propeller collet onto the motor. This is a clamping type of propeller collet, so once I tighten the prop nut, it clamps down onto the motor shaft. Repeat this for all 4 motors and props. Make sure that they're tight, hold the motor in place, and try and spin the props. You should feel a lot of resistance. Also make sure you put the correct props on each motor in the props in configuration. Once complete, it should look like this. Let's get ready for the first test flight. The battery is going to slide into the frame. I'm securing it with some gel tape and a Velcro battery strap. For this very first flight, I'd highly recommend flying on a grassy field so that there's a soft place to crash in case of any issues. Keep a finger on the disarm button just in case you need to quickly disarm. The main purpose of this first test flight is to verify that the motors are all spinning in the right direction, that the props are on the right way, and that the flight controller orientation is all correct. If everything is okay, the drone should fly. If it spins out uncontrollably, then one of these is incorrect and you should go back and double check all the connections. You can also use this time to practice flying line of sight, which is tougher than it looks. Maintaining orientation is a skill that doesn't really come naturally. So this test flight is complete. The next step is to add the GPS module. I'm using the HDLRC M100 module. It has a 6-pin connector port. The SpeedyV mini flight controller, it comes with a 6-pin cable that's half assembled. This is because GPSs, they don't have a standard pinout, so it's up to us to insert the pins correctly. The already assembled end of the cable will plug right into the flight controller, while the end we're assembling now will go into the M100 GPS. Here's the order to put the wires: black, red, yellow, white, blue, and green. Plug this end that we just made into the M100 GPS. Once it's complete, it should look like this. Insert the other end of the cable into the flight controller as I'm doing here. I'm spinning the wire around to coil it and keep it tidy. Now I need to mount the GPS in a place that's away from the other electronics so it gets a clean signal from the satellites. To do this, I'm designing a GPS mounting plate and 3D printing it. This is a simple plate with 2 holes, so if you don't have a 3D printer, you can make one yourself from wood or plastic. Use 2 long standoffs to mount the plate above the flight controller. Then use double-sided sticky gel tape to mount the GPS module on top of the plate. Make sure that the antenna points towards the sky. Also, make sure to mount the GPS exactly in this orientation with the wire coming out the right side of the drone. That's because there's a compass on this module, and so the drone needs to know exactly where it's pointed, and this orientation, with the wires coming out the right, is the default orientation. Now that the GPS is mounted, it's time to set it up in INAV Configurator. Earlier in our port section, UART3 should have already been set to GPS. That's good. Let's go over to the configuration tab and we can finalize the GPS setup. So first, this GPS unit has a magnetometer. It's the QMC5883. So under magnetometer, we're going to select that one, QMC5883. And also under here, we're going to find Enable GPS for navigation and telemetry. That means we are going to use the GPS module, so we're going to check that. So those are the 2 things we need to change. Make sure the magnetometer is selected and make sure the GPS is selected. And then we're going to hit save and reboot. Next, now that we have our magnetometer selected, we have to calibrate it. The magnetometer is also the compass, so we go over to calibration. Once I hit calibrate compass, I'm going to have 30 seconds to rotate the drone around to make sure that the compass gets close to all of the directions. So that's what I'm going to do. I'm going to hit calibrate compass and start spinning the drone. Alright, I've calibrated my compass, so I'm going to hit save and reboot. And we go back up to the status page, we can see that all of our pre-arming checks are completed. All the calibration has been done, runtime calibration, everything is a green check mark, which means we're good to go. Last thing we want to do is in our modes tab, we want to actually set GPS position hold because by default, it's not going to do that. So what we want to do is earlier we set adjust the arming and angle mode on channels 5 and 6 respectively. And so what we're going to do is we're going to scroll down to navigation position hold and we're going to add range to channel 7. And once again, set that to our upper range. Then we're also going to enable nav altitude hold also on channel 7. So altitude hold and position hold, they're both going to be active at the same time. Then I'm going to hit save. On our GPS tab, we should ideally be able to see the GPS location, but unfortunately, because I'm inside, I'm not getting a good GPS signal. Now here, I'm using the default settings, which uses the satellites from the USA. This works great for me, but if you live somewhere else, you may want to enable the other options as well. This GPS screen is also where you can set up waypoints if you want to do automated waypoint navigation missions. To double check our alignment of our GPS unit, can actually go over it down here to show our GPS unit respective to our drone. So if we can select that, we can see the default layout, and that's what we have matched over here. So the front of the drone is pointed up towards there, and the cable coming out of the GPS is coming out of the right. And that's the same exact way we mounted it in the drone. And of course, if you mounted it in some other way, then you're able to rotate it around here and change it. to make it easier, I just did the default, and that's what I'm just going to leave it at, so I'm not going to save anything. So as just one final sanity check, let's hit save and reboot. And now it's time for a GPS test flight. So first, power on the transmitter.
Welcome to HTX.
And then I'm going to plug in power to the drone. Now, if I try and arm it right now, it's actually not going to arm. That's because now that we have GPS enabled, it's not going to arm until it has a GPS satellite lock. And to check that, I can actually go into my telemetry screen. So model, let's go back a page into telemetry. And here we can see all of our telemetry options. And let's go down to GPS. So we can see we don't have any GPS coordinates, and our satellite, SATS, is 0. Alright, I'm at 10 satellites, so I'm good to take off. This thing is going to take off until I get at least 6 satellites, but 10 is plenty, so we're good to take off. And my position hold switch is this one up here, but I'm not going to take off in position hold, so I'm going to first fly in angle mode up to where I want to stay, and then I'm going to engage position hold afterwards. I can also bring up my battery in the telemetry screen. It's at 12.5 volts, it's almost fully charged. Let's go ahead and take off. Alright, let's get a little bit of altitude, and then I'm going to go ahead and I'm going to engage my position hold button, and so it should stay in one place. So right now I'm still manually flying it, I'm at full control. Now let's go into position hold. And now it's holding position on its own. You can let go of the stick, and it's going to stay in roughly the same position. I'm still in control of the altitude, so if I bring the throttle down, it's going to go down. And if I bring the throttle up, it's still going to go up. So to maintain altitude, I'm going to maintain my position, my stick position, roughly in the center there. But yep, it is holding position with no input besides the throttle. And it's starting to rain, so I'm going to land actually right now. Alright, so that's the first brief little tutorial on how to fly with GPS position holds. Now it's time to add the fun stuff, the airdropping mechanism. I'm using a standard size servo, the MG995, and I have it set up on the bench here with the servo tester. I'm adjusting it so that at the center position, the pin is halfway open, and at 1000 the pin is all the way closed, and at 2000 the pin is all the way open. We can fine tune this later in INAV, so you don't have to be super precise about this. To attach the mechanism, I'm taking off the bottom plate of the drone so I can screw in some screws from the inside. I'm using these thin profile M3 by 8mm screws. And while I'm attaching the plate back on, it's a good time to install the long landing gear legs if you haven't already. These legs come with longer screws that'll replace the screws on the bottom of the frame. For each arm, unscrew the 2 stock screws, align the landing gear legs over the holes, and use the 2 longer screws for each arm and attach it into place. Repeat this for all 4 legs. Now there's a lot of room under the drone for our gadgets. Here's a better idea of what the dropper looks like now that we have more room. I'm using the servo tester to test out the pin release mechanism. It's pretty neat. Oh yeah, and once we're done testing, don't forget to plug in the servo from the airdropper into the flight controller. Plug it into port S5, which is next to the speed controller plugs. Now let's get back into INAV configurator to set up this servo. Alright, the drone is plugged into INAV configurator, and just one little thing, the servo isn't going to be powered unless there's battery power going into the drone. So right now I have the battery connected to the drone, which is why it reads 12.24 volts, and once the battery is connected, then I connected the USB cable, and now it's recognized in INAV configurator. And setting up the servo is really simple. We're just going to go over here to the mixer tab, and earlier we plugged our servo into S5, and so that's where we want our servo to be. So S5 is timer 8, so under timer 8 I'm going to put it under servos. And then I'm going to scroll down here to servo mixer. We have to add that servo in, so we're going to add a new mixer rule. We have servo 1, and the input is just going to be our RC channel number 8, because 5 is arm, 6 is angle mode, 7 is position hold, and so our servo release mechanism we're going to tie to channel 8. That's the next one that's free. And for the weight, this is like how much range the servo has, and 100 is actually quite a lot. For me at least, I found that 75% was a good amount. You can play around with this value as well. And so I'm going to hit save and reboot. Alright, that's done, and I already set up my radio beforehand, so if I look at channel 8, I have that set. So this is closed at 1000 and 2000. It's going to open, and I can hear the servo actuating. So yeah, that's it. That's all we need to do to enable our servo dropping mechanism. So now let's go out and try it out. Alright, so here's what I'm dropping. It's a water bottle on a string with a tiny little loop on it. So the loop is going to go as I was testing it out, someone decided to park right next to me. I'm guessing his car is a rental, or hopefully it is. What I quickly learned was that a heavy payload at the bottom of a long string, it creates a strong pendulum effect, so the drone trying to stabilize and the payload, they can get into like a synchronized oscillation that makes it pretty difficult to control. To fix this, I tied the string shorter so that the pendulum is shorter and it won't oscillate as much. It flies a lot better now. Let's bring it up in the air and drop it. 3, 2, 1, drop. That was kind of cool, but the plastic bottle is just too strong. Also, this 2-pound bottle is pretty much the carrying limit for this drone, so let's go for a different payload. Alright, let's change things up. Let's drop a can of soda. Three, 2, 1, drop. Alright, that was pretty cool. And that's it, our $150 drone platform is done. What I like about this build is that it strikes a balance. It's affordable, it's capable, and it leaves room for you to make it your own. Whether that means adding a camera for FPV or trying different payloads, this is a platform that you can grow and experiment with. And there's just something about seeing all the parts you've put together take flight for the first time that makes it all worth it. If you decide to build this yourself, I'd love to see what you come up with. And if you enjoyed this video, I'd really appreciate it if you could subscribe to my YouTube channel. Thanks for watching, and I'll see you in the next build.